This is Physics 2212 Lab 6 Magnetic Braking with Faraday. So the purpose of this lab is to explore the phenomena observed when a powerful magnet falls through a conductive non-ferrous tube by using Faraday's law. The main principles were Faraday's law, Ohm's law, Lorentz law, Watt's law, and Newton's second and third law. The system found was to be the bar magnet tube, while the surroundings were everything else. And the result was found to be that the average fall time is 1.16 seconds, and the computational fall time is 6.512 seconds, which will be explained later. Here you can see all the fundamental principles, such as Faraday's law of induction that defines how to find the induced EMF, Lorentz law, which defines how to find force based on the current and the length times the cross product of magnetic field, Ohm's law, which defines the electric current based on voltage and resistance, Watt's law, which is how to find the magnetic field, Newton's second law, which is force is equal to mass times acceleration, and Newton's third law, which states that every action is equal to it, has an equal and opposite reaction. Here you can see what the materials used were, which was a smartphone, bar magnet, roll of aluminum foil, and a mirror stick. And the procedure was to just hold the tube vertically and record dropping the magnet through the tube. Repeating this 5 times, we then calculated the average time for the magnet to fall through the length of the tube. The experiment results we found were there to be the tube length was equal to 0.3 meters, the foil width was equal to 0.006 meters, the tube inner radius was found to be 0.027 meters, the magnet mass was found to be 0.023 kilograms, the magnetic dipole moment, which we grabbed from lab 4, we found was to be 13.342 amps times m squared, which this answer is the likely reason our computational model was so wrong. And then the average time we found when dropping the magnet to the tube is 1.16 seconds. Part 1 of our glow script code, you can see our constants where we just define what our length, width, inner radius, mass, and magnetic moment are. For part 2 of our code, we define functions to find the magnetic field and the magnetic flux. So here in part 3 of the code, you can see in step 4 that we use Ohm's law to find out the current of a ring of the tube. And then in step 5 and 6, you can see that we use Lorentz law to find the force on the magnet. And then note that this is for a small area of the tube. And then lastly, in part 4 of the code, you can see that we use Newton's law where we find out the gravitational force, and then we found out the net force by adding the gravitational force plus the magnetic force. And then we just find out the velocity of the bar in step 8. And then here you can see the results. We found that the amount of time it took based on the model was 6.312 seconds, which is obviously wrong, and it's because of what we found in lab 4 for our magnetic moment. Based on the graph, you can see its velocity versus time. At the start, you can see that it's because the force of gravity is greater than the magnetic force. In the middle, you can see that velocity does not change, so that means that the gravitational force is equal to the magnetic force, and at the bottom you can see that the gravitational force overcomes the magnetic force, and so it drops. So the assumptions that we made was that the magnet is aligned with the tube. In reality, there would most likely be a torque that rotates the magnet. Another assumption is that the only forces are magnetic field and gravity, but this would probably not be the case because another force would be something like friction. Potential errors would be exterior forces, such as friction, and then also inaccurate measurements, such as what we found for the magnetic moment. So to interpret the simulation, which color corresponds to the clockwise current and which counterclockwise? How can you know? So red is clockwise while blue is counterclockwise because north was on the top of the magnet, so the bottom current must have a dipole moment that points away to repel the magnet, while blue would be the opposite, so it will want to attract the magnet. What happens to the dynamics of the system when you flip the magnet around? The current directions would just be the opposite, so red would be counterclockwise and blue would be clockwise. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? So in real world, it will take longer because of forces like friction. The computational system can also include torque and other forces like friction. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So we already talked about this at the start and end. The gravitational force is stronger. In the middle, both are equal. So the final questions would be, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the following magnetic chains. So Ohm's law states that the current will increase to keep voltage the same, and then thus there would be a stronger magnetic force, which would cause the magnet to fall slowly. Lastly, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? We modeled the currents to be multiple closed loops. Holes will cause there to be less rings and thus some to be a smaller magnetic force and will cause the magnet to fall faster. Then that is all. Thank you.